steel coils are transported and loaded onto the production line using magnet lifters. These lifters are equipped with powerful magnets that securely hold and move the steel coils, ensuring efficiency and safety during the loading process. Once the steel coils are in place, they pass through an edge milling machine. This machine trims the edges of the coils, removing any irregularities or imperfections. After edge milling, the steel coils move to the pre-bender machine. This machine shapes the coils into a U-shape, preparing them for the subsequent bending and welding processes. The U-shaped steel coils are then fed into the in-feeder machine. This machine guides the coils into the JCO, J-ing, C-ing, and O-ing press bending machine, which is the heart of the pipe-making process. The JCO press bending machine is a critical component in the manufacturing of steel pipes. It uses a combination of hydraulic and mechanical forces to bend the U-shaped steel coils into the desired pipe shape. After the steel coil has undergone the JCO bending process, a turning transfer car is used to rotate and position the pipe correctly for the subsequent welding steps. Tack welding is the first step in joining the edges of the steel coil to form a continuous pipe. A tack welding machine temporarily holds the edges together with small welds. The inside welding machine is responsible for making the longitudinal seam weld on the inside of the pipe. It uses a high-frequency welding process to fuse the edges of the steel coil together. Once the inside welding is complete, any excess weld material or beads are removed from the inside of the pipe using a back bead cutting machine. The outside welding machine performs a similar function to the inside welding machine, but on the external surface of the pipe. It creates a longitudinal seam weld on the outside, enhancing the pipe's structural integrity. The A-way machine, also known as the impending machine, further shapes the pipe and ensures its dimensional accuracy. The end-facing machine is used to trim and square the ends of the steel pipe. A washing device is used to clean the pipe's external surface, removing any debris or residue left from the manufacturing process. The last step in the manufacturing process involves using an X-ray test machine to inspect the weld seams for any defects or anomalies. Production process begins with steel bar cutting. High-quality, corrosion-resistant steel bars are precisely cut to the required length, following specific dimensions and guidelines to ensure uniformity and accuracy. After cutting, the steel bars undergo a heading process, where the ends are shaped to accommodate the subsequent steps. Next, multiple layers of high-strength steel wire are coiled around the prepared steel bars at an accelerated rate. This wire wrapping reinforces the structural integrity of the pile, allowing it to withstand heavy loads and provide excellent tensile strength. Once the steel bars are wrapped with the high-strength wire, they are transferred to the case and shoe assembly section. Here, a specialized case and shoe structure is assembled around the coiled bars, forming the outer shell of the concrete pile. After the assembly, the prepared piles are moved to the concrete input part, where they are carefully positioned for the next crucial step. High-strength concrete, specifically engineered for durability and load-bearing capabilities, is poured into the prepared molds, encapsulating the coiled steel bars. The next step involves covering the concrete-filled cases to protect the piles during the curing process. This covering ensures that the concrete remains undisturbed and retains its strength as it hardens. Once the cases are covered, the piles are transferred to the bolt tightening section. This stage plays a pivotal role in the pre-stressing process. In this step, specialized bolts are securely fastened to the end of the steel bars. These bolts will later be tensioned to induce compression in the concrete, enhancing the pile's load-bearing capacity. The piles, now equipped with tension bolts, are moved to the steel bar tensioning section. High tensile forces are applied to the steel bars by tightening the bolts. This pre-stressing operation imparts compressive forces within the concrete, making the piles even more robust and capable of withstanding heavy loads and forces. With the steel bars pre-stressed, the piles are transferred to the rotary molding stage, where they receive their final shape and finishing touches. The piles are carefully transported to a steam chamber, which provides the ideal curing environment. Inside the steam chamber, the piles undergo curing for approximately 12 hours. Once the curing process is complete, the piles are transferred to the demolding section. At this stage, the outer casing is removed. The outer casing is carefully removed from the concrete pile, revealing the final product. The pile's surface may be inspected for quality and aesthetics. Finally, the pre-tensioned bolts are removed, leaving behind a pre-stressed, high-strength concrete pile ready for use in various construction applications. The production of precast concrete piles is a carefully orchestrated process that begins with the procurement of essential raw materials, such as cement, sand, aggregates, and water. Once the raw materials are deemed suitable, they are transported to a batching plant, which is equipped with modern equipment designed to mix them in precise proportions according to a specified mix design. Precast drainage production involves the use of molds to create various drainage components, including pipes and manholes. The molds are filled with the precisely mixed concrete, and the concrete is allowed to cure within the molds. After the curing period, the final products are carefully demolded, inspected for quality, and prepared for transportation to construction sites. For the production of precast concrete piles, two distinct methods are employed: spun production and solid production. In the spun production method, a steel cage is placed within a cylindrical mold and the concrete mix is poured in. To compact the concrete around the steel cage, centrifugal force is applied, ensuring uniform density and strength. Once the spinning process is complete, the precast concrete pile is allowed to cure within the mold. After curing, it is cut to the desired length and prepared for transportation and installation at construction sites. This method is ideal for creating cylindrical concrete piles with consistent properties. The solid production method, similar to the spun production, also involves pouring a precisely mixed concrete mix into a mold. However, unlike spun production, the concrete is allowed to cure within the mold without the use of centrifugal force. Once the curing process is complete, the solid concrete pile is demolded, inspected for quality, and prepared for transportation and use in construction projects. The production of precast concrete piles is a highly controlled and efficient process that results in durable and reliable construction components. By following these steps and adhering to strict quality control measures, precast concrete piles are manufactured to meet the stringent demands of various construction applications. The manufacturing process of steel pipes, especially large diameter pipes, is a crucial part of the global oil and gas industry. TMK, one of the world's leading producers of steel pipes and pipe solutions for the oil and gas sector, plays a significant role in this industry. Let's delve into the manufacturing process of these steel pipes, including the technology and quality control measures they employ. TMK operates several production facilities to meet the demands of the industry. Large diameter pipes, LDP, are manufactured at the Borscht Give pipeline and service feed tube works, and their total annual production capacity is approximately 1 million ton. TMK is known for being Russia's only producer of large diameter spiral pipes and for operating the world's only facility with DP heat treatment equipment. Heat treatment is a critical step in the manufacturing process of steel pipes, as it helps to adjust the mechanical properties and microstructure of the welded seam, heat-affected zone, and the base metal. This process ensures that the characteristics of the pipes become similar to those of seamless pipes, which are highly sought after in the industry. By investing in DP heat treatment equipment, TMK can provide pipes of exceptional quality. TMK employs a continuous automated production process that allows them to manufacture pipes with high precision in terms of geometry, diameter, outer roundness, curvature, and weld quality. This precision is essential to meet the stringent requirements of the oil and gas industry. TMK produces two main types of steel pipes: longitudinal and spiral pipes. Longitudinal pipes. These are manufactured using roll forming followed by submerged arc welding and expanding. This technology is highly efficient and advanced, making it suitable for producing large diameter longitudinal pipes. The longitudinal pipe mill at TMK has an annual capacity of 650,000 tons per year and can produce pipes ranging from 508 to 1420 millimeters in diameter, with wall thicknesses ranging from 7.9 to 42 millimeters. These pipes can have steel grades of up to X100 and conform to API 5L specifications. Spiral pipes. The submerged arc welding pipe mill produces spiral pipes with diameters ranging from 532 to 1420 millimeters and wall thicknesses between 6 to 60 millimeters. These spiral pipes are used in some of the largest oil and gas pipelines in Russia and the CIS, including projects like the Caspian Pipeline Consortium, Kinky Arc Atirau, Baltic Pipeline System, Female Europe, Central Asia Center, Chantry Preserve, and many more. Ensuring the highest quality of products is a top priority for TMK. To achieve this, all TMK plants have implemented a quality management system compliant with ISO 9001 and an environmental management system compliant with ISO 14001. Furthermore, all large diameter pipes undergo rigorous non-destructive testing, including ultrasonic, X-ray, magnetic particle inspection, and hydraulic testing. TMK's pipes are coated to enhance their durability and protect against corrosion. They offer different types of coatings, including external corrosion-resistant coating. TMK provides 2-layer polyethylene or polypropylene coating and 3-layer polyethylene or polypropylene coating for large diameter pipes. These coatings ensure the durability of underground pipelines, even in extreme temperatures ranging from -60 degrees Celsius to +80 degrees Celsius for at least 30 years. Inner coatings. TMK also offers inner coatings for large diameter pipes, including anti-friction and protective coatings. These coatings are essential for various applications, such as gas pipelines, drinking water pipelines, agricultural water supply, and sewage systems. The durability of pipelines with these coatings can range from 10 years to several decades, depending on the specific application and operating conditions. Over the years, TMK has accumulated significant experience in supplying large diameter pipes to major projects for companies like Gazprom and Transneft. These projects include pipelines like Avenue Volga, Nord Stream, Baltic Pipeline System, Power of Siberia, and many others. TMK's production processes are well suited for such large-scale projects, and they aim to continue participating in new tenders and pipeline projects.
C300, or reinforced concrete cylinder pipe, is a robust and reliable type of concrete pressure pipe. Its structural elements consist of a steel cylinder, steel reinforcement, or cages, and concrete. The manufacturing process of C300 starts with a steel sheet that is used to create a welded steel cylinder. This cylinder is fabricated to the desired length, and steel joint rings are welded to both ends. To ensure the weld's integrity and watertightness, a hydrostatic test is performed. The steel reinforcement or cages are then constructed using welded wire fabric or steel rods through a cage-making machine. An electronic arm on the machine moves a single rod in a continuous spiral along the longitudinal rods, and automatic welds are made at each intersection. Once the cage reaches the design length, it is separated and transported to the concrete placement area. Before placing concrete, these newly formed steel reinforcements or cages are positioned outside the steel cylinder. Inner and outer forms are used to encase the cylinder and cages. Concrete, batched according to a specified design mix, is placed in the forms, filling the annular space between them. After concrete placement, the pipe is placed in a curing cell for elevated temperature curing with steam. After the initial cure, the formwork is removed. Once the concrete reaches the specified compressive strength, the pipe is ready to be shipped and placed into service. C301, or pre-stressed concrete cylinder pipe, is another important type of concrete pressure pipe. Its structural elements include a steel cylinder, a concrete core, pre-stressing wire, and a mortar coating. The manufacturing process of C301 shares some similarities with C300. It begins with the fabrication of a steel cylinder using steel sheets, followed by welding steel joint rings to both ends and conducting a hydrostatic test to verify the weld strength and water tightness. Next, the steel cylinder is lined with concrete for lined cylinder pipe, or embedded in concrete for embedded cylinder pipe. After this initial step, the pipe undergoes elevated temperature curing with steam. Once the concrete reaches sufficient strength, pre-stressing wire is attached to the exterior of the pipe at one end and wrapped under controlled tension and spacing from one end to the other. Simultaneously, a cement slurry is applied to the exterior. The pipe, now wrapped with pre-stressing wire, is mounted on a revolver and rotated while a machine applies the second application of cement slurry to create the mortar coating. After the mortar cures, the pipe is ready to be shipped and placed into service. C302, or reinforced concrete pressure pipe, differs from the previous types in that it does not include a steel cylinder. Instead, the structural integrity of the pipe wall is provided by steel reinforcement or cages, similar to C300. The manufacturing process of C302 involves the construction of steel reinforcement or cages using welded wire fabric or steel rods, as demonstrated in the video. These cages are placed concentrically over an inside form, and an outer form is centered over them. Concrete, batched according to a specified design mix, is then placed to fill the annular space between the inner and outer forms. After concrete placement, the pipe undergoes curing at ambient or elevated temperatures. Once the concrete reaches the specified compressive strength, the formwork is removed, and the pipe is ready to be shipped and placed into service. C303, or bar-wrapped concrete pressure pipe, shares structural elements with the lined cylinder version of C301, including a steel cylinder, a concrete core, wrapped reinforcement, and a mortar coating. The manufacturing process of C303 starts with the fabrication of a steel cylinder from steel sheets, followed by welding steel joint rings to both ends and conducting a hydrostatic test. Stiffener rings are placed around the cylinder to ensure roundness before it is transported to the lining area. In the lining area, a mortar lining is applied using a centrifugal process. After this, the pipe is placed in a cure cell for elevated temperature curing with steam. Once curing is complete, the stiffener rings are removed, and the lined cylinder is prepared for the final stages of the process. Unlike C301, which uses pre-stressing wire, C303 is wrapped with mild steel bars. The bars are wrapped around the cylinder at uniform spacing while a cement slurry is applied along the exterior. The bar-wrapped cylinder is mechanically rotated to ensure uniform coating with the second application of cement slurry, creating the final cement mortar coating. After curing at ambient or elevated temperatures, plastic end caps are attached to keep the pipe's interior moist for large diameter pipes. Steel pipes have been an essential component of various industries for over a century, known for their strength and durability. Tenaris, a leading name in the steel pipe manufacturing industry, has consistently pushed the boundaries of seamless pipe production. This commitment to innovation and environmental responsibility has culminated in their state-of-the-art seamless pipe manufacturing plant in Bay City. Let's delve into the three crucial steps that set Tenaris apart in the seamless pipe manufacturing process: hot rolling, heat treatment, and finishing. The journey of creating a seamless pipe begins with solid steel bars, which are meticulously cut into billets of precise weight. These billets are then loaded into a natural gas-powered rotary hearth furnace and heated to a scorching temperature ranging from 1,250 to 1,280 degrees Celsius. The intense heat transforms the steel into a hollow bloom using a process known as the Mannesmann effect. The hollow bloom proceeds to the premium quality finishing mill, where it is elongated. Following this, it enters an induction furnace for homogenization of temperature before entering the stretch-reducing mill. In this step, the outside diameter of the pipe is carefully reduced to match the specific requirements of the end customer. Ensuring the hardness and toughness of the steel pipe is crucial, and this is achieved through the heat treatment process. It starts in the austenitizing furnace, where the pipe is reheated above the austenite transformation temperature. The pipe then enters the quenching process, where water sprays rapidly cool it from approximately 900 degrees Celsius to ambient temperature. This rapid cooling causes a phase transformation in the steel, resulting in a very strong but brittle martensitic phase. To restore ductility and adjust mechanical properties to the required range, the pipe undergoes reheating in a tempering furnace. Following this, the pipe moves to the resizing machine to achieve precise dimensional tolerances before straightening, eliminating any ovalization. In the final stage, the pipe goes through rigorous testing and verification to ensure it meets Tenaris's stringent quality standards and the specific requirements of the customer. First, hydrostatic testing is performed to guarantee that the pipe can withstand specified pressure requirements. Next, an electromagnetic inspection is conducted to detect defects internally and externally. Ultrasonic testing is then employed for precise wall thickness measurement. The pipe is faced and beveled to facilitate the threading process. During threading, an automated rotating headstock ensures uniform threads, which are visually inspected and dimensionally controlled by advanced inspection equipment. Specialized automated equipment is utilized during coupling and makeup to achieve the final pipe and coupling joint. A drift test is conducted to ensure there won't be any clogging within the pipe. The pipes are then treated with lacquer and/or varnish to prevent corrosion during storage or transportation. Measuring, weighing, and stenciling are carried out to identify each pipe based on the heat and pipe number, meeting all marking requirements through Tenaris's pipe tracer technology. Finally, the pipes are automatically bundled and prepared for delivery to their designated service centers, ready for distribution to customers.
Welcome to the heart of wind turbine production at the GE Renewable Energy Plant in Pensacola, Florida. This sprawling facility spans 800,000 square feet, 50% of which is dedicated outdoor space. Mo Maddox, the executive plant manager, proudly leads a workforce of 600 employees across 3 shifts, all united by a singular mission: to be the world's premier provider of cost-effective clean wind energy components. GE Pensacola stands as a beacon of innovation and efficiency, crafting machine heads, hubs, and drivetrains for various wind turbine models. The team's success is rooted in 3 fundamental pillars: prioritizing team safety, fostering diversity and inclusion, and driving excellence through lean and continuous improvement. Transitioning from batch production to assembly lines in 2016 marked a pivotal transformation. This shift significantly reduced inventory, increased production efficiency, and optimized assembly processes. Now, the plant boasts the capability to produce over 100 turbine assemblies weekly, a testament to their commitment to lean principles. The workforce, comprising dedicated individuals like Ken Jones, the site production leader, embodies the plant's unique culture. GE Pensacola fosters an environment where every employee, regardless of their role, has opportunities for growth and contribution. This inclusive and collaborative atmosphere fosters a shared goal of advancing clean energy while cherishing camaraderie among coworkers. The assembly of the first tower elements for the Cypress onshore wind turbine involves aligning and securing the tower sections, typically comprising precast concrete or steel segments. Each section must be precisely fitted and anchored to ensure structural stability, forming the foundation for the turbine's height and stability. The nacelle lift involves hoisting the turbine's housing unit atop the tower using specialized cranes with precise positioning mechanisms. The drivetrain and hub connection involves intricately linking the gearbox, rotor shaft, and hub to enable power transmission and rotation. The combined lift integrates the drivetrain, hub, and nacelle roof, hoisting them simultaneously to streamline the assembly atop the tower with coordinated precision and efficiency. Lowering the drivetrain into the nacelle involves carefully positioning and securing the assembled components within the housing unit. The single-blade installation is a meticulous process where each aerodynamic blade is attached individually to the hub. A crane or specialized equipment precisely positions and secures the blade onto the hub, ensuring accurate alignment and balance. This step demands careful calibration to maintain optimal blade pitch and aerodynamic efficiency. Quality checks are critical to confirm secure attachment, as the blades are crucial for harnessing wind energy efficiently. Tower assembly is a crucial stage in erecting a wind turbine, ensuring it stands tall and sturdy to harness the power of the wind effectively. General Electric, GE, employs a process to construct these towers, customizing them to withstand diverse wind conditions and maximize energy production. GE begins by fabricating tower sections in specialized manufacturing facilities. These sections are crafted with precision, usually using high-grade steel due to its strength and durability. The dimensions of each section are carefully engineered to fit seamlessly during assembly. Once the sections are ready, they undergo stringent quality checks to ensure they meet GE's exacting standards. Subsequently, they are loaded onto transport vehicles and carefully shipped to the designated wind farm site. At the wind farm site, a coordinated effort begins to assemble the tower sections. Heavy machinery, including cranes specifically designed for lifting these colossal components, is employed. Each tower section, weighing several tons, is hoisted into place by the crane. Bolts, nuts, and flanges, precisely engineered for this purpose, are used to securely fasten the sections together. This process demands utmost precision to guarantee the structural integrity of the tower. Safety is paramount throughout the assembly process. Rigorous safety protocols are followed, and specialized safety equipment is used to ensure the well-being of the workers involved in this challenging task. Additionally, the assembly area is carefully cordoned off and monitored to prevent accidents. Once the tower reaches its intended height, it serves as the support structure for the installation of the nacelle and rotor assembly. The precision in constructing the tower is crucial, as it determines the stability and performance of the entire wind turbine system. The nacelle, a critical component housing the turbine's key machinery like the gearbox, generator, and control systems, arrives at the site. Utilizing a robust crane, skilled technicians lift and secure the nacelle onto the tower. This precision is vital to ensure a snug and secure fit atop the tower, laying the foundation for the efficient functioning of the wind turbine. The installation of the rotor assembly marks a pivotal phase in the construction of a wind turbine. Comprising blades and a hub, the rotor is the primary component responsible for capturing wind energy. GE's blades are crafted using advanced materials like fiberglass or composite materials. These materials offer exceptional durability and efficiency in capturing wind energy. The manufacturing process involves precise molding and quality checks to ensure each blade meets stringent standards. Once fabricated, these blades undergo meticulous quality inspections before transportation. Transporting these oversized components demands specialized logistics to ensure their safe delivery to the wind farm site. Simultaneously, the hub, a central component to which the blades will be attached, undergoes its assembly process. The hub is engineered to withstand immense forces and facilitate the connection of the blades. It's transported to the site along with the blades, ready for integration. Upon arrival at the site, the blade attachment process begins. Skilled technicians, equipped with specialized tools and safety gear, carefully handle the blades. A crane, tailored for heavy lifting and precise maneuvering, assists in positioning each blade for attachment. The connection between the blade and the hub demands attention to detail. Specialized bolts and equipment designed for this specific purpose are used. Each blade is aligned with precision to ensure optimal aerodynamic performance and balanced distribution of forces. Throughout the installation, stringent safety protocols are observed. Workers undergo comprehensive safety training, and the installation area is rigorously monitored to prevent accidents. Simultaneously, engineers conduct continuous quality checks. They inspect the blade connections, verifying torque levels, alignment, and structural integrity. Any discrepancies are swiftly addressed to guarantee the reliability and safety of the rotor assembly. Dynamic balancing, a critical step, ensures the rotor operates smoothly. This process involves fine-tuning the blade alignment to minimize vibrations, thereby enhancing the turbine's efficiency and longevity. Advanced tools and techniques are employed to achieve the desired balance. Once all blades are securely attached to the hub and the dynamic balancing is complete, the assembled rotor undergoes a comprehensive inspection. Every aspect, from the integrity of connections to the aerodynamic alignment, is meticulously evaluated. Subsequently, the rotor assembly is integrated with the nacelle atop the tower. A heavy-duty crane carefully lifts the rotor assembly and mounts it onto the already installed nacelle. This process demands precision and coordination to ensure a seamless fit and proper alignment. The removal of underground fuel storage tanks, like those at the 7-Eleven on Western Avenue, is a significant process that involves steps and considerations. In this case, the tanks were being dismantled because they were no longer in use, prompting concerns about environmental safety. The abrupt closure of the convenience store raised eyebrows, leaving the property seemingly abandoned. Brian Bannon, the Brattleboro zoning administrator, noted the sudden departure, emphasizing the importance of proper dismantling for safety and environmental protection. Efficient tank removal involves a series of precautions. First and foremost, the tanks must be emptied of any remaining oil or fuel. Failure to do so poses severe risks, including potential fires or explosions during the demolition process. This aspect highlights the criticality of draining the tanks before any excavation work begins. Interestingly, the concern about the removal process arose when the LLC owning the property contacted Bannon, expressing worries about the tank removal occurring without their consent. However, since gas tanks are regulated by the state, local approval wasn't necessary for this project. The ownership of the tanks lay with 7-Eleven, which had decided to discontinue selling gas. Ted Uncles, the coordinator of the Underground Storage Program for the Vermont Agency of Natural Resources Department of Environmental Conservation, provided insights into the process. He mentioned the scheduled removal of the tanks by 7-Eleven and the involvement of an environmental consultant, emphasizing the importance of assessing soil for any evidence of petroleum compounds leakage. The tanks, installed in 1994 with subsequent piping added in 2009, were significant in capacity, holding thousands of gallons. Multinational engineering company AECOM was tasked with handling the removal process, ensuring environmental safety standards were met. Uncles also highlighted that if no problems were found post-removal, there would be no restrictions on future development on the property. However, in severe cases of contamination, restrictions might be imposed on the deed. Fortunately, major cleanup issues were relatively rare in such removal projects. Despite the closure and tank removal, the future of the property remained uncertain. Speculations about new tenants were vague, with no immediate plans for occupancy. Attempts to reach out to both 7-Eleven corporate and the store itself were unsuccessful, adding to the mystery surrounding the site's future. The LLC's owner, John Warner, established the entity in 2012, but contact information was not readily available, further shrouding the situation in mystery. As the property stood in a state of transition, various stakeholders, from zoning administrators to local association presidents, sought information about the property's fate. The concern was not just about the removal process, but also about the potential future development or usage of the site. The Casa Finance City Tower stands tall in the heart of Casablanca, Morocco, a soaring testament to the city's ambition and growth in the realm of international finance. Rising 122 meters above the bustling streets, this architectural marvel embodies the vision of the Casablanca Finance City Authority, the driving force behind the city's burgeoning business district. The authority, dedicated to propelling the development of a new financial hub, entrusted the construction of its headquarters to Bimero, marking a pivotal step in the realization of their grand plan. Situated within a sprawling new district exclusively tailored for global finance, this tower is a cornerstone, set to grace 320 hectares of land and accommodate over 1 million square meters of office space upon completion. Capturing every moment of this monumental construction endeavor is TenarisBayCity, a pioneering leader in the field of visual construction monitoring solutions. Their comprehensive services span the globe, offering not just installation but also on-site maintenance, seamless internet integration, and the expertise in crafting captivating time-lapse films that encapsulate the evolution of these ambitious projects. At the heart of TenarisBayCity's arsenal lies their proprietary self-contained photo units. These cutting-edge devices operate wirelessly, powered by solar energy and equipped with 3G capabilities. They oversee a state-of-the-art Nikon reflex camera, diligently capturing hundreds of high-resolution images daily. Through an intuitive web interface, stakeholders witness the construction's daily progression, fostering transparency and informed decision-making. Tailored for the rigors of outdoor environments, DeviceUbox finds its niche primarily within the construction and building sector. Its reliability in providing real-time, high-quality visual data makes it an indispensable tool for tracking and documenting the intricate stages of projects like the Casa Finance City Tower. Begin by safely shutting off the existing dispensers. Ensure proper safety protocols are followed. Once shut off, open the dispensers to release any remaining pressure or product. Carefully disconnect the piping from the existing dispensers. This step requires precision to avoid spills or leaks, ensuring the environment remains safe and clean. Similarly, disconnect the electrical connections from the dispensers, ensuring power sources are safely turned off before handling any wiring. Unload the new Wayne dispensers, ensuring they are handled with care to avoid any damage during transportation and installation. Remove the old Gilbarco dispensers systematically, clearing the space for the installation of the new ones. Proper disposal or recycling of old dispensers is important and should be in line with environmental regulations. Prepare the island for the installation of the new dispensers. This involves ensuring the surface is clean, level, and ready to support the new equipment. Carefully position the new dispensers in their designated locations. Reconnect the piping, ensuring a secure and leak-free connection. Anchor the dispensers securely to the ground to ensure stability and safety. Apply caulking around the dispenser base to seal any gaps and prevent moisture or debris from entering. Complete the necessary terminations of electrical connections, ensuring proper wiring and safety measures are in place. Purge the system to remove any air or contaminants from the piping and ensure a clean flow of fuel. Calibrate the dispensers to accurately measure and dispense the intended volume of fuel. Configure the dispensers according to the specifications and requirements of the station or client. Apply necessary decals or branding to the dispensers, ensuring they are properly labeled and compliant with regulations. Conduct a thorough cleanup of the installation area, removing any debris or materials, Ensure all tools and equipment are accounted for and properly stored.
The construction begins by establishing the exact location for the board piles. Theodolites, like the Kyoto light, are employed to calculate angles and horizontal distances, ensuring precise placement based on approval drawings. Using an auger pulpit machine, a primary hole is initially drilled to a depth of approximately 20 to 30 meters. A steel casing with a depth of 16 meters is inserted into the borehole using a vibrating hammer. The vertical accuracy of the steel casing is verified using a plumb bob during installation. Protecting the borehole. When the primary hole is drilled, it's essential to maintain its integrity. The temporary steel casing is inserted to prevent the borehole from collapsing or caving in, especially in unstable or loose soil conditions. This protective casing ensures that the borehole remains open and intact during the construction process. Vertical accuracy. The steel casing provides vertical accuracy. It is checked using a plumb bob during the installation process to ensure that the borehole is precisely aligned, both for depth and verticality. This accuracy is crucial for maintaining the structural integrity of the pile. Maintaining borehole shape. The steel casing helps maintain the shape of the borehole, ensuring it remains consistent and uniform throughout its depth. This uniformity is essential to ensure that the subsequent concrete filling or other construction materials are deposited evenly and smoothly, avoiding any irregularities in the board pile. Preventing soil contamination. In cases where the surrounding soil might be contaminated, the steel casing acts as a barrier, preventing contact between the soil and the construction material used for the board pile, such as concrete. This containment helps ensure the stability and safety of the construction. Pressure maintenance. The primary role of polymeric slurry is to maintain consistent pressure in the surrounding soil during drilling. This pressure prevents soil collapse or caving, ensuring the borehole's stability. Lubrication and cooling. Polymeric slurry serves as a lubricant for the drilling process, reducing friction and wear on equipment. It also cools the drilling bit, preventing overheating. Soil removal. The slurry assists in removing excavated soil from the borehole, facilitating efficient drilling and preventing blockages. Contaminant control. In cases of soil contamination, the slurry acts as a barrier, preventing contaminants from escaping into the environment. Welding the reinforcement steel casing is a crucial process in board pile construction. It involves the secure attachment of steel reinforcements to the casing, ensuring the structural integrity of the board pile. This welding process typically employs high-strength welding techniques, electric arc welding. The reinforcement cage, when affixed to the casing, provides the necessary strength to withstand the structural loads imposed on the pile. Typically, this cage consists of interconnected steel bars or rods that provide structural strength to the board pile. It is carefully lowered into the bored hole after the completion of drilling and the removal of the temporary steel casing. The cage is positioned to the specified depth, ensuring that it remains securely in place, thus reinforcing the pile and allowing it to withstand the anticipated loads and forces it will bear once construction is complete. The insertion of the tremie tube is a crucial phase in board pile construction. The tremie tube, made of robust materials, is carefully lowered into the borehole after the reinforcement cage is in place. It extends from the pile's surface to the bottom, ensuring that concrete is deposited evenly from the base to the top. The tremie tube helps prevent the mixing of concrete with any water, slurry, or contaminants in the borehole, ensuring the structural integrity of the board pile as it cures from the bottom up. Once the tremie tube is in place, concrete is introduced into the borehole. It is poured from the bottom to the top, displacing any water or slurry within the tube. This method ensures that the concrete fills the borehole uniformly, and the pressure from the polymeric slurry forces excess slurry to rise, preventing any voids or irregularities. Proper concrete pouring is essential to the structural integrity and load-bearing capacity of the board pile. The construction of a pier typically begins with the fabrication of reinforcement bars, commonly known as rebar. Rebar is a vital component of any structural project, as it provides tensile strength to concrete structures, ensuring they can withstand the forces of nature and the test of time. The first step in rebar fabrication is determining the specific requirements of the project, including the size, shape, and spacing of the rebar. The engineer or project manager calculates the required quantity and specifications of the rebar based on the design of the pier. This includes assessing factors like the load-bearing capacity, environmental conditions, and the type of soil or seabed the pier will be anchored in. Once the specifications are determined, rebar is then fabricated according to these requirements. This process involves cutting and bending steel rods to create the desired shapes and sizes. The next phase of pier fabrication is excavation. This step involves preparing the ground where the pier will be constructed. The excavation process may vary depending on the location and environmental factors, but it generally includes the following key steps: site preparation. Before excavation begins, the site is thoroughly cleared of any obstacles, debris, or vegetation. This includes removing rocks, roots, and any other materials that may hinder the excavation process. Surveying. Precise surveying is conducted to mark the exact dimensions and layout of the pier. This is critical for ensuring the pier's alignment and positioning meet the project's specifications. The depth and size of the excavation depend on the design and engineering plans. Soil samples may be collected and tested to assess their load-bearing capacity and suitability for pier construction. The results of soil testing help determine if any additional measures are needed to stabilize the foundation. Once the excavation is complete, the next step is the installation of the rebar. The rebar serves as the structural skeleton of the pier, reinforcing the concrete and ensuring its strength and durability. The installation process involves several critical steps. Setting rebar frames. The prefabricated rebar pieces are assembled into frames according to the project's design. These frames are placed at precise locations within the excavated area to create the reinforcement structure for the pier. Securing rebar. The rebar frames are securely tied together at intersections using tie wire to maintain their position during concrete pouring. Proper spacing and alignment are essential to ensure the pier's structural integrity. Lifting and positioning. Larger or heavier rebar frames may require the use of cranes or other lifting equipment to position them accurately within the excavation. Embedding in footings. In some designs, rebar may extend into concrete footings or pilings to provide additional stability and anchorage for the pier. Splicing is the process of joining two rebar pieces together to ensure the continuous reinforcement of the pier's structure. Splicing is essential when the length of rebar required exceeds the standard size available. The following are common methods of splicing rebar. Lap splice. In a lap splice, the ends of two rebar pieces are overlapped and then secured together using tie wire or mechanical couplers. The length of overlap is typically specified in the project's engineering plans. Mechanical couplers. Mechanical couplers are prefabricated devices designed to connect two rebar pieces securely. These couplers are threaded or serrated to provide maximum strength. Splicing must be done in accordance with the project's design and engineering requirements. Properly spliced rebar ensures the structural integrity of the pier especially in areas subject to high loads and stress. Before proceeding to the final step of concrete pouring, thorough testing of the concrete mix is essential. The quality of the concrete used in the construction of the pier is critical to its longevity and performance. Concrete testing involves several important aspects. Batch testing. The concrete mix is prepared in batches, and each batch is tested for its compressive strength, workability, and consistency. This ensures that the concrete meets the required standards and specifications. Formwork is the foundation of the concrete pouring process. It provides the necessary structure to shape and contain the concrete while it's in its liquid state. Wooden or metal formwork is used, with the choice depending on the specific requirements of the project. The formwork follows the design and dimensions of the pier precisely, ensuring that the concrete takes on the desired shape. Formwork also plays a crucial role in preventing concrete spillage and maintaining the structural integrity of the pier during the pouring process. Transporting the concrete mix to the construction site is a critical logistical consideration. The method used depends on the distance of the construction site from the concrete production facility and its accessibility. In many cases, concrete mixers are employed to transport the mixture to the site. However, when dealing with long distances or challenging terrain, concrete pumps may be used to efficiently deliver the concrete mix to the precise location within the formwork. Once the concrete mix reaches the site, the placement phase begins. Concrete is carefully poured into the prepared excavation, filling the formwork and covering the rebar frames. The precise and even distribution of concrete is essential to ensure structural uniformity and strength. To achieve this, skilled workers use tools such as vibrators and trowels. Vibrators are used to eliminate air voids and improve the concrete's density, reducing the risk of weak spots or potential structural defects. Trowels are used to finish the surface and create a smooth, even texture. The meticulous work of the concrete placement phase is critical for the structural integrity of the pier. Curing is a fundamental process that follows concrete pouring. It's the method of maintaining the proper conditions of temperature, moisture, and time to allow the concrete to harden and gain its maximum strength. Proper curing is crucial as it enhances the concrete's durability, reduces the risk of cracking, and ensures it reaches its specified compressive strength. Various curing methods can be employed, such as covering the concrete with wet burlap, plastic sheeting, or using curing compounds. The choice of curing method depends on environmental conditions, project requirements, and the type of concrete mix used. Curing usually continues for a specific duration to achieve the desired concrete strength and resilience. Their mission: to lay the foundation for a high-rise hospitality tower on the bustling corner of Figueroa and Pico, a prominent intersection in the heart of the city. The magnitude of this undertaking was immediately evident, as it was poised to bring a massive influx of hospitality to the area, adding 727 luxurious hotel rooms across the street from the Los Angeles Convention Center, meeting the city's ever-growing demands for accommodations. The construction day began in the early hours, with national ready-mix trucks converging on the site as the clock struck 1 a.m. The steady hum of engines and the beeping of reversing vehicles filled the air, setting the stage for a day of groundbreaking progress. The pour was a monumental task, requiring a precise and coordinated effort, as 7,096 cubic yards of concrete had to be expertly distributed. A total of 7 concrete pumps worked tirelessly over the course of an exhausting 11 hours to complete the colossal task. The pouring of the concrete marked a pivotal moment in the project, as it symbolized the solid foundation upon which the high-rise tower would rise. The scale of the pour was awe-inspiring, a testament to the dedication and expertise of the construction team, and a symbol of the determination to make the project a resounding success. As the tower began to take shape, the guest rooms were strategically distributed across the upper 28 floors. These rooms would offer breathtaking views of the city, from the iconic skyline to the shimmering lights of downtown Los Angeles. Their design and amenities would undoubtedly cater to the needs and desires of the discerning travelers and convention-goers who would soon be calling this place home. In addition to the luxurious guest rooms, the building incorporated 8 parking levels, ensuring that visitors would have easy access to the hotel. Convenience and accessibility were key elements in the design, reflecting the modern traveler's expectations. At street level, a sprawling 11,000 square feet of retail space was destined to create a bustling hub of activity. This space would undoubtedly house a variety of shops, restaurants, and services, adding to the vibrant and dynamic character of the area. Passers-by and guests alike would have the opportunity to explore and enjoy the retail offerings, further enhancing the appeal of the hospitality tower.